Traditional compute infrastructure relies on the CPU, which uses a few powerful cores built for sequential processing, executing tasks one after another. A GPU takes a different approach, utilizing thousands of specialized smaller cores to execute massive mathematical operations simultaneously in parallel. The current surge in generative AI is a hardware story as much as a software one. NVIDIA's specific architecture is what enables the massive volume of calculations required for deep learning. Managing this environment requires a specialized four-layer architectural stack: the hardware, the CUDA engine, infrastructure operations, and workload deployment. We are going to construct this stack from the ground up, starting with the microscopic silicon die and building all the way to a deployed inference server. Mastering AI engineering requires understanding how these four layers link together to feed raw data into the processors. We begin at the hardware layer. AI infrastructure starts at the physical, microscopic layout of the silicon die. Modern GPU architectures, like Ada Lovelace, divide computational labor among highly specialized compute units, including standard CUDA cores and ray tracing cores. But the essential mathematical engine for modern deep learning is the Tensor Core. Tensor Cores are purpose-built to execute mixed precision matrix math, like FP16 and BF16. They run these specific operations at speeds that standard cores cannot match. How that silicon is packaged dictates its use case, dividing the hardware into consumer and enterprise scales. Consumer RTX cards provide the standard hardware environment for local development and basic isolated model inference. Production AI deployments scale up to massive DGX systems and clusters of H100s in the enterprise data center. Inside these clusters, the GPUs are interlinked using NVLink, providing the high-speed data throughput required for training large language models. The exact physical arrangement of this hardware determines whether a system is suited for prototyping on a single machine or executing massive, multi-node production workloads. All of that parallel hardware is useless without an API to control it. NVIDIA's solution is CUDA, the defining software abstraction layer that makes general-purpose GPU computing possible. Through the CUDA Deep Neural Network Library, or cuDNN, this bridge provides seamless integration with high-level software frameworks like PyTorch and TensorFlow. The CPU sends an operation to the GPU. This workload breaks into execution units called threads. Threads bundle into groups of 32, forming a warp. Multiple warps collect into a block, which are scheduled to the streaming multiprocessors. Achieving maximum parallel performance relies on managing the memory hierarchy across the device, moving data from ultra-fast thread registers all the way down to the slower global VRAM. Without this rigorous CUDA hierarchy mapping software instructions directly to the physical silicon, the GPU's immense processing power would devolve into operational chaos. With the software actively communicating with the hardware, the infrastructure manager must monitor system health, driver configurations, and workload allocation. The NVIDIA SMI interface is the primary telemetry tool. Executing daemon displays real-time power metrics, while Query GPU enables targeted data extraction into a CSV output for logging. In an enterprise environment, dedicating a massive, high-capacity GPU, like an H100, to a single lightweight inference task wastes valuable compute resources. The hardware solution to this resource problem is the multi-instance GPU, or MIG. MIG physically slices the GPU into up to 7 distinct partitions. This allows multiple models to run concurrently with strict hardware isolation, preventing memory or compute interference between them. Telemetry monitoring and MIG partitioning convert a monolithic, single-use piece of hardware into a highly optimized, multi-tenant enterprise resource. The top layer of the stack handles deployment. Enterprise AI workloads must be isolated, reproducible, and ready to scale. Standard Docker containers operate completely isolated from the host operating system, meaning by default, they cannot access the physical GPU hardware. The NVIDIA Container Toolkit acts as a critical bridge, injecting the GPU driver namespace into the isolated container. Installed above the base OS and bare metal drivers, the toolkit triggers via configuration flags, allocating the hardware directly. Once the container has direct hardware access, the application layer takes over, using deployment systems like the Triton Inference Server. Triton manages incoming prediction requests, serving deployed models, like a ResNet vision model, reliably at scale. Proper orchestration through the container toolkit ensures that a model built and tested on a local RTX card deploys seamlessly across an entire DGX cluster. NVIDIA provides a fully integrated computing pipeline. The base relies on silicon packed with Tensor Cores, designed to execute rapid matrix math. That math is scheduled and controlled by the CUDA abstraction hierarchy of threads and blocks. The physical hardware is continuously monitored via SMI telemetry and cleanly partitioned using MIG instances, and the models themselves are delivered to the hardware via GPU-aware container orchestration. True AI infrastructure engineering is the rigorous practice of eliminating bottlenecks across this precise stack, ensuring that the world's most powerful silicon is never left waiting for data.